Our senior design project consists on the creation of a solar cell characterization device, which is named SCCD. The main factor that motivated our group to pursue the assembly of a device of this nature arises from the ever-growing need around the globe to switch from non-renewable sources of energy to renewable sources of energy, which for us translates to a more widespread use of solar cells. The device is modeled based on the already existing models of a solar cell device and has 4 subsystems, which are the microcontroller, the impedance analyzer module, the LabVIEW interface, and the 3D hardware design. The main purpose of it is to characterize a given solar cell sample by obtaining descriptive readings from said sample that will be provided through the use of LEDs and the 4 subsystems working together.
The microcontroller will be employed to gather, analyze, and interpret the required and necessary measurements for the solar cell impedance analysis. This chip empowers system designer to optimize the device for power consumption versus processing speed. Some of the features this chip provides are 6 pulse width modulation channels, programmable serial USART, 23 programmable I/O lines, and operating voltage from 1.8 to 5.5 volts. The microcontroller will obtain a live feedback from the impedance analyzer module to be used in the LabVIEW for final characterization of the solar cell.
For the impedance analyzer, we're using the PMOD-IA module, which has an onboard analog to digital converter and a frequency generator with an operating frequency limit of 16 MHz. It is also capable of measuring impedances from 100 ohms to 10 mega ohms, and it has an I2C communication protocol, as well as a programmable frequency sweep and gain amplifier. The module will be connected to the solar cell sample through coaxial cables, which will be connected to the SMA connectors. And it has compatible code libraries available to access and modify scripts in order to be synchronized to the microcontroller and the LabVIEW interface. Here we have Arduino code for the impedance analyzer that we were able to create. All these lines of coding. And the sketch has been running for a while already. If you click the serial monitor, you can see all the values that we're getting. We're getting values for frequency, impedance, magnitude, and phase. That it's constantly updating every 5 seconds. And from here, we're going to export these values to the LabVIEW interface, and in the LabVIEW interface, we'll be able to represent the results through the Nyquist plot.
The user will be able to use the LabVIEW's front panel to adjust the frequency, amplitude, phase, and offset of the sine wave that is used to control the LED lights, which is based on pulse width modulation. The LEDs are used to emit light on the solar cell, and as a result, we shall obtain a Nyquist plot and a Bode plot. A Nyquist plot describes the gain and phase of a frequency response in polar coordinates by plotting the imaginary part of the complex frequency response versus the real part. A Bode plot contains a Bode magnitude plot and a Bode phase plot. These 2 plots together describe the frequency response of the system. The following figure shows an example of a Bode magnitude plot and a Bode phase plot.